Good morning, everyone. This is a recording for October 27th, Text Mining Part 2. The part that you're listening right now actually is remade after October 27th because we're having some equipment problem during our class time. So then, as we know that before we have the break, and quite many students have difficulty to listen to me online clearly because my voices was cut off from time to time. So we are apologize for it. And then because of it, so let me try to revisit all the material we try to cover around that time. Okay, so then here is outline for October 27th. So we will start to having the QA, and then afterward, we will try to talking about some traditional method on how to identify the text relationship, including to find the name entity and to find the reference or co-reference, the relationship between the name entities. And then afterward, we are going to talk about the language model. And then, as you know, right now, many people, when they're working with the machine learning, they're all talking about the large language model. So we are going to talk about some basic concept for those language model, including the first version of the language model by utilizing recurrent neural networks. And then afterward, the very fundamental transformer. And then after that, is some technique that we try to working on, that including BERT, ChatGPT. But as I know, because of the equipment problem, we have difficulty to move as fast as I expected. So then we only cover to the BERT part. Okay, so here are the questions that people ask during the 1 minute reflection for the October 13th. And then the one question I think is quite important is they have difficulty to differentiate between the skip gram model and the continuous back of words model in the word2vec, because you know the word2vec have these two different models. So let me try to utilize these two different statements right here. One statement is called, "This is a marvelous movie theater." And then there's another statement called, "This is a good movie theater." And so then you can actually see the left sentence and the right sentence only having one word different: marvelous and good. Okay, and then you can also know that most people utilize the adjective good instead of marvelous, because marvelous is more like a real word. And in the continuous back of word model, what they did is they utilized the surrounding word, so that we call them context word, as input. So for example, right here, the context word will be "is a movie theater." So there are the left parts and the right parts right here, next to the marvelous. Okay, and in the continuous back of word model right here, they will utilize marvelous as answer. Okay, but then you actually were thinking about these two different statements, you will realize that if I input "is a" and a movie theater, okay, and then I have two possible answers. One is marvelous, one is good. However, because the chances that we try to having good is a lot more than marvelous, so it will be very likely in the end if we say, okay, here is input data. I apologize. This shouldn't be here. Okay, this actually belong to the next statement. So let me try to remove them. And then if I having this "is a movie theater," and then the continuous backward model probably was thinking about, are they marvelous or are they good? Because both of the answer actually exist. So it'll be very likely in the end, they actually were thinking the good actually is more likely to be the answer for is a movie theater. In other words, if they thinking good will be the answer, which means that the encoding that the vector we learn from the continuous backward model for marvelous will not be that accurate because they don't really know the relationship from marvelous to what kind of word. Okay, so then skip gram model actually try to solve that problem by just exchange the answer to become input and then input to be an answer. So then in skip gram model, they will utilize marvelous as an input. And then when you input marvelous, and then try to guessing what will be the answer, then we say here is the answer, is a movie theater. So in that cases, we don't need to worry what our model actually got confused. What will be the answer? Because when you actually input marvelous to get the answer of is a movie theater, will not very different from good and to get the answer of is a movie theater. And since their answer are the same, okay, so it will be very, very likely in the end that the skip gram model with thinking maybe marvelous and good are having the similar meaning. Okay, so that is why at the time when they design the word to vec, they will have this skip gram model and the continuous backward model try to learn together, and then afterward they try to aggregate the answer to get our the vector we expect to have. So that try to address the answer. What is the difference between skip gram model and the continuous backward model? Okay. So next question will be come from some student because it's also related to word to vec. What are the input dimension of the continuous backward model in the word to vec? Okay, so then if you can thinking about that, so that let me try to give you certain keyword. So we can having if you've never heard about this keyword before, we apologize for it. It's called corpus. Okay, in the linguistic. And then we consider our data set. We give them some, if the data set consists of the text, we usually call them corpus. Okay, so then in our corpus, in our training data or testing data set, and then we know that the number of the word in our corpus, we have the size of n. So we have n different word and different token in our corpus. In that cases, and because each word actually is one dimension. Because based on our one hot encoding before, every word right here is like one dimension. So in that cases, or our continuous in our word to vec, our input dimension will have the size of n. Each one of them corresponding to one of the keyword. Okay, so that is the input dimension, the size of the continuous backward model. What actually totally depends on the vocabulary size. Okay, so the next one, what would be the initialization value of the word to vec training data? Okay, then you need to know at the very beginning. So let's try to go back to this illustration. Here, assume this is a neural network. Okay, because continuous backward model or skip gram model for the word to vec, actually they were having this kind of neural network. So what they usually did is all the age actually starts in a random way. So they initially set up all the value in a random way and then go through the different training data, and then the weight are starting to change. And after we see all the loss actually getting very small, and then we already make our learning almost complete, and then we can get those hidden factors that we're talking about. So then they all start randomly. And then, but when we start randomly, we will actually try to train them and to make the vector or the weight actually become better. So after we know the weight, so next time, if I am going to train something differently, but I don't want to start from scratch, I can utilize some parameter value that we trained before, and then we directly copy them. In that cases, if we directly copy them, we kind of already have all the wisdoms being trained like last time. So for example, let's try to see these two trending. So assuming the left figure actually spin trend. Okay, so all the value right here on the edges, actually we already get a very good value for it. So then we actually did not trend for anything. Next time, I'm going to working on something else. This one, I don't want to start the value initially with random value. So I can directly utilize their value and copy them. So we directly copy them and to this new neural network. And then afterward, that the neural network actually will be performed as the same as the left-hand side one, because you know that when our weighting actually being set up correctly, we can kind of already having the Wilson copy paste from the our left neural network. Okay, so then by that, you can actually know the neural network is quite easy for us to copy the information from one to another. That is also the same approach people try to do that right now. Okay, but we probably were talking about that later on when we try to go over for the language model. Okay, so then some students are also asking that professor that speed further today, that for October 13 or like on September 29, say the speed for today is too fast. I have to apologize for that. And because we have quite many topics and that we try to cover for the session. And so I apologize, I cannot slow them down. Okay, and I also apologize. Sometimes I will see some certain student actually say, Professor, I don't really understand some concept about A or some concept about B. Can you repeat them again? Usually I will mention some concept again. If most of the students do not understand them, then I will try to prepare my material, actually utilize different example, different illustration to talking about them. But if there's only one or two students say they don't understand some of the topic, rest of them say they are clear, then you probably need to rewatch the video. But when you try to rewatch the video, maybe you can tune your video in the slower speed and then make the speed actually slower. Okay, then right here, we also want to show that to you. For here is the syllabus from our TAICA courses, Natural Language Processing from Professor Gao Hongyu. And then you can actually see, actually I already removed the part that for their final project in their 18-week space of the syllabus. And then you will actually find out they have 1, 2, 3, 4, 5, 6, 7, 7 weeks about the material we want to cover in these 3 weeks. But in these 3 weeks about the text mining, we even having like 1 hour try to go for the progress. So in other words, that there are too many things that we can cover, but we unfortunately we don't have the time to go over for them. So each part of the concept, I probably can go to the very, very brief and in a fundamental and overview way. Okay, I apologize for that. But if you actually after our the 3 weeks session, you find it's quite interesting, you want to go deeper, and then you can take the NLP courses to get more detail in there. Okay, so then before I moving on, okay, and here is an NTU cool exercise, allow you to know again to compare the TF-IDF backward approaches with the word-to-vec way. So that try to work on it. So you can pause your this video and try to working on it. And then here, because we already having some student answer the question in the class, so let me try to go through this question again. So which of the following implementation of the TF-IDF backward? Okay, so if you see BOW without actually try to confuse with the the word to vec one. So try to know if we mention TF-IDF back word model, and then what is the difference as compared to the word to vec? Okay, so first things, okay, TF-IDF back word model, they are suffer a lot from their dimension in TF-IDF back word is quite high because each dimension represent a word they selected after TF-IDF. And then because of it, we usually mention the TF-IDF backward approaches as sparse representation. We mentioned this keyword last time. Okay, that try to remind you again. But the word to vec, we actually having certain thing, we call them dense representation. Most of the machine flavor language model, we usually call them dense representation. A dense representation means the dimension actually is a lot lower than the TF-IDF backward approach. Okay, so the first one was right. The second one, the inability to capture the semantic meaning between the word, because in the TF-IDF backward model, even though you have the word like good and marvelous, but then for the TF-IDF, they consider they are totally two different dimensions. So they don't actually thinking they are the same. But in word to vec, we can utilize a vector to compare how similar they are. Okay, and handling the misspelled words in word to vec, we do not care about it. But maybe the problem can be solved by the large language model. Okay, so then the next one, label the context preservation between adjacent words. Because the TF-IDF did not say, oh, if you see marvelous, and let me try to thinking about what are the words surrounding by that. No, they just actually pack this old bag right here and say that is one dimension. And afterward, I don't really care about all the context surrounding by those bag. Okay, so there are 1, 2, 3 right here. Okay, next one. Why is word to vec often preferred over traditional TFF back of word model for certain tasks? Why word to vec actually is more preferred in certain tasks? First thing, because it's a dense representation. So you can actually reduce the possibility to suffer from the curse of dimensionality. Okay, the second one was not right because we say focus solely on term frequency, ignoring the document frequency. No, because word to vec actually is not only prefer the term frequency, and no, not related to that, because TF-IDF actually pay attention to term frequency and document frequency. But word to vec actually we utilize certain things more implicitly, not directly utilize that part. Okay, the third one, yes, it certainly was right because it can capture the semantic relationship between the word. Okay, so then the word to vec actually did not actually consider in binary manner, so that is why we did not consider that answer. Okay, so the last question, match the advantage of disadvantage of the corresponding technique. Okay, capture the semantic relationship between the word, then yes, you need to know that belong to the word to vec. Second, represent the word as discrete entity in high dimensional space. That supposedly related to back of word approaches for TF-IDF. Next one, provide a continuous vector space for word representation. That because if you see some vector space, spatially is continuous vector space, that is for word to vec. And the next one, maintain context by considering the surrounding word. Only word to vec actually care about that. Okay, next one, treat each word as independent entity without considering the surrounding word. Actually, it's kind of conflict from the previous one, right? So that is TF-IDF backward approach. The last one, fail to capture the semantic meaning between the word. Again, that supposedly should be related to backward. So if you are the person that actually makes certain mistake and then you have difficulty to understand, please remember to go back to the previous recording. Okay, so then let's try to move on. The part that we want to talking about, we want to give you some of the technique utilized by some traditional natural language processing. The reason why we still want to introduce them, because some of the technique or some of the important problem actually are still being reused in different way. That is why we want to mention about that again. Okay, so then in the there's like synthetic parsing, we actually talking about that related. So after you have the pause tagging, you can go to do some parsing and do the synthetic parsing. But we don't want to say how we want to do with it. Just remember that term. And for today's session, we want to talking about non-entity extraction and call reference resolution. So what are non-entity recognition? Is if you have some document. Let me see. Okay, sorry, I don't have them right here. If you have a document, and then, for example, here is one document. Okay, so inside this document, can you identify which part of them actually refer to some non-entity, refer to some individual, organization, location? That is a non-entity we're talking about. Okay, so if you can find that, and then, so sometimes when people actually mention about an entity, for example, they can do Kansas, okay, they can do Jayhawks, and sometimes actually they might having the different way to mention about them. So if you find them, try to identify what are the span from which character to which character. Okay, probably we can say, okay, see, from right here in this statement, okay, and the first 1, 2, 3, 4, 5, 6, the first 6 statement, except for that bullet, actually is the exact span to talking about Kansas. So that is a span, what we meant. And after you find that, you get the Kansas, then the next one is try to classify which category they belong to. Okay, so that is non-entity recognition. Not only find the name, also recognize what type of the name that we actually try to identify. So what are the non-entity type we can consider? They could become people, they could become organization, they could be location or like a geopolitical entity or facility or vehicle or something other, some other type we did not mention, but you think they are important. That would be fine too. So for example, you can actually see the example right here, say like Turing is often considered to be the father of the modern computer science. So then right here, Turing is a named entity, okay? Or like right here, the updated Mini Cooper retain its charm and agility. So then right here, the Mini Cooper, this span right here, actually identify another named entity. Okay, so but when we try to do the classify about an entity, we see the next problem. Because sometimes, so for example, Washington, when you see Washington, what you can thinking of? You probably can thinking about President Washington, okay? Or you can thinking about some location, Washington State, or you can thinking about Washington, D.C., that is a political entity people try to mention to refer the government of the United States. Or actually, some people will say, Washington Mutual organize the bank. So that will be about some organization. So you can actually thinking about Washington can be really referred to different kind of category. Okay, so then because of it, sometimes people will have difficulty to identify which category it belongs to. So sometimes we might need certain context word to help us to understand, oh, this Washington is more related to location. That Washington, because we say the Washington, and afterward we see he, blah, 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 then we understand, oh, that Washington would be regarding to person. So you can actually see, in order to disambiguous about the type, quite many researchers are actually thinking about the context word to help with it. Okay, so then how to make this name entity recognition in perform in better way? And they have two different type of the approach. One is more rule-based approach, and one is more like machine learning approach. We don't want to talk more about machine learning because we already talking about classifier last time. You can directly thinking about that. But right here, we want to show something to you that is called regular expression. Okay, regular expression are very fundamental in computer science, especially when people want to process certain corpus and want to know which part of them are telephone. Okay, from human being, we understand how the telephone number looks like. So for example, we see this one is a telephone number. Here we also understand here's another telephone number. And then right here, we actually thinking about there's another telephone number. So they are all possible. Okay, so in that cases, we probably can say, oh, the telephone number actually can write here. You can have a certain digit right here. And then afterward, you can have another digit right here. So that are the possible way we can thinking about the telephone number. Okay, so then we can also say the software name actually will utilize this different way. And then after that, you can identify this one as a software name. Okay, and if you want to know more about the regular expression, you can check the corresponding reference. I mean, if you can directly just Google the regular expression, I believe you can find a lot of rule right there. But the reason we don't want to actually tell you how to do the regular expression, we just want to introduce a term. If that is needed, you can actually find the corresponding reference and then see and try to learn by yourself how to utilize the regular expression. Okay, next one, we want to talking about another term called call reference resolution. And the call reference resolution is, again, very similar to an entity definition, is we want to find the entity in the text. But then you probably say, but right here is the entity. The previous one, named entity recognition, you also having the entity. What's the difference between them? So let's try to see this example. Here are a paragraph. Before I talk, and maybe you can actually try to check on it a little bit. And then afterward, let me try to tell you that we try to highlight some parts in this text, like right here. This unwritten language. Unwritten language can be considered as some entity. Okay, but then which part of them are also referred to this entity, such as they, one, and so many things are actually referred to it. So when I try to know that, oh, which part of the span actually is related to unwritten language, okay, then you actually will realize it's not just about language or it's not just about unwritten language. All the word that is related to it, that like one, they are really like this one should also refer to it. So that is why we call them call reference resolution, because when you see this they, you need to find out where they try to refer to. Okay, so common approaches for us to do that. First, we can utilize some handwritten pattern to knowing that, oh, when I actually see the language right here, when we see car right here, and then how people usually try to refer to the car. Okay, and then we can also do some supervised way. But today, the reason we still try to mention about that is because when we having some corpus, a lot of document, then you might realize that utilize pure machine learning, maybe from the large language model, it probably will still lack of something. So you still need to utilize more like supervised way to working on it. However, that most of the time when we're thinking about supervised learning approaches, you are thinking about you need to get so many informations being annotated, but I just don't have this huge training data set. So what to do with it? We want to introduce approach called bootstrapping approach. So what does that mean? Oh, by the way, later on, I will talking about bootstrapping. I'm too eager to tell you. And in the 2024, and then our student actually, after we go through the entity recognition and call reference resolution, they just say, Professor, I'm sorry. I don't really understand what's the difference between them. Okay, so let us try to utilize one example to show this one to you. Right here, you have a statement. Apple are red, violet are blue. Both of them are pleasing to look. One of these things is my favorite. Okay, so when we have the name entity recognition, we identify which part of the name are name entity, such as apple, violet, and then afterward, in the name entity recognition, I'm not only trying to identify apple and violet, I also would say their category. Okay, like fruits is a category for apple. Flower is a category for violet. Okay, so that are name entity recognition. But then right here, because I did not see any explicit name, so we can done with this part. But when we try to do the co-reference resolution, we need to do one thing is, for example, okay, and then like right here, I see they, right here, you can see them, but you can just imagine we can somehow have a way to convert them to they. And what are this one? This one are referred to apple and violets. Okay, that is called reference resolution. When I see something, I need to know which one is corresponding to it. And I need to know what is the words, the relationship between one to another. So they have different ways. Sometimes people will utilize a rule, sometimes people utilize a pattern. So we want to introduce one thing we think is quite interesting. So there are quite many researchers working very hard to knowing that we have different kind of name entity. And in order for us to know the relationship between an name entity, we might need to actually construct different type of the relationship between them. So this researcher Harsis actually say we can have different kind of the relationship. One of the relationship is called ISA, like apple is kind of fruit. So that is a relationship. Okay, so in order for us to know that is a relationship, we can have different pattern, such as Y, such as X. Okay, so which means X is a Y, right? Because right here you can say fruit such as apples. So then you will know apple is kind of fruit. Okay, so such Y as X. So you can actually see if I want to find this is a, I can have X or other Y, X and other Y, Y including X, Y especially X. All of them are referred to X is a Y. Okay, right here. Let me try to, right here, you can actually see all of them actually say X is a Y. Okay, so I can utilize a rule to specify something like that. So next time, why this one is important? If I have the rule like that next time, and then I see the pattern, I see such as, then I can directly convert all the relationship between X and the Y. Actually, their relationship type is a. If I actually saw and X and other Y, so I saw this and other thing, then I can actually directly assign an is a relationship between this X and the Y. Okay, so that is why some researchers actually working on the pattern. But because human being like diversity. So sometimes when we try to write certain thing, we would try to work very, very hard to produce different variation of writing the same thing. So sometimes we, not sometimes, most of the time, we cannot exhaustively, explicitly list all the possibility. So then how can we working with that? We can starting. So this is a very useful strategy. Okay, so sometimes when my students try to working on research, there are lack of the data set. I always ask them to go to refer to our slides, okay, and in the text mining part. That is called relation bootstrapping mechanism. And then the one of the reason I still keep those slides, I did not really remove them because if you see the Professor Gao's NLP courses, you will find out I actually already removed them. He already removed them. I did not remove that part because I find out it's quite useful, especially if we lack of the training data. So we can do the bootstrapping mechanism. So what are the bootstrapping mechanism? You can imagine that we can having certain things, we call them seed. This part of them are seed. Seed could be very, very small set of them. And from my seed, okay, I can actually get more information because the seed allow me to identify some other information from the yellow part. And from that yellow part, I probably can also expand to get a bigger one. Okay. So until like, so for example, in the end, I find out that if I extend further, that probably are not accurate. But I can actually starting from seed, this green part, and to enlarge them into the blue part. So what I did in the bootstrapping is I have some seed, okay, and then I try to find some sentence that contain that seed. And then afterward, we're looking for the context. You actually will find out the terminology context actually show up in many different places. Why? Because contexts are really, really important. We kind of mentioned that last time in our discussion. And then right here, you can also see them again. So let me try to utilize an example right here. Okay, so assume I actually have a seed tuple called Mark Twain and Elmira, okay, that actually try to refer to the relationship between the person, Mark Twain, he actually was buried in Elmira. Okay, but then if I actually already know that relationship, I already can specify here is a relationship between Mark Twain and Elmira. The problem for me is I don't really understand what is the context word surrounding by it. So what can we do is we can grab, for example, Google, okay, do some information searching in my corpus and find out all the sentence actually contain these two keywords. Like right here, Mark Twain, Elmira, here Mark Twain, and Elmira. And then actually, I don't care about the order. Just assume if I don't care about the order. So I can get these three different statements. After the three different statements, then I try to mark what are my context words between this X and the Y. So for example, here are the context words between Mark Twain and Elmira. And then here are the context words between Mark Twain and Elmira. And here is the context word between Mark Twain and Elmira. So then afterward, that become pattern, right? So the next time I actually can utilize this pattern is buried in Y, and then go to searching in a Google to see that's who actually having that pair. So for example, if I actually do this one, okay, go to the Google, okay, and then so you will actually will find out that who is buried in the Pentagon. Then right here, actually you will have a different part of people. So then right here, that is a lot. So then afterward, you actually can utilize the next sentence right here. I'll try to find some information such as Annabelle Carcio. I don't really know who he is. Or the King Mirasing and with Peterson. And then afterward, you can actually utilize these two different pair and then try to grab more pattern. So that is what it means from this bootstrapping mechanism. Okay, so then afterward, you can do this iteration and getting more and more like what we try to show and make our corpus getting bigger and bigger. And sometimes some people probably are asking that, but where I can get this seed? I don't know the seed. Can I get more seed? Yes, you could. Actually, in the world, in our World Wide Web right now, if you go to Wikipedia, okay, and then you will find out Wikipedia have in something we call an info box. So, for example, right here, let me try to do some search. So if I want to search engine and then search for Wikipedia and Trump, okay, he's a very famous person right now, okay, and then you actually will find out in these pages right here, we're having a box. This is a box, and that is where I actually get right here, okay. Oh, by the way, so you can actually see my screenshot was a little bit outdated right now. Trump right here already having the 45th and the 47th president of United States. So there are all the information right here. Okay, so then you can see proceed by and succeed by, and they have a lot of things. So then Donald Trump, this person, Donald Trump, and the relationship, he has for example, precede by relationship with another entity, Barack Obama. Okay, so then that is how you can get the C right here from Wikipedia info box. And while we actually try to emphasize on Wikipedia info box, then do that again right here. Because if you directly try to process that information, you probably don't know the pattern, right? But then the info box is some human being already identify some relationship type right here. So you will not get much wrong from that information. So they can become very good seed. Okay, so then next one, we are going to talking about a very important concept called language model. Okay, so why we want to talking about the language model? Because it is a very important trend in the current NLP. You can actually find out, just like what we show from Professor Gao Hongyu's class, a lot of material are about all the language model way. And but there's one important concept, what is called language model. You can imagine is some very huge neural network, very huge one. Okay, and then you actually will see from our language model, we're talking about something very confusing, because you will heard about certain thing called pre-trained model. Pre-trained model. What does that mean? Pre-trained model usually means that just do that again. So for example, right here, assume this is a neural network, okay, a huge neural network. And then we try to train them. And after that, we get the very low loss value, and then make things getting better and all the precision and thing getting high. So we consider our model was done. Okay, so then this black box afterward, okay, we can have all the parameter values being fixed and then provide to other people. So you can imagine the company A. So the company, let me try to do company A, try to working on that model. And when company A working on the model, they did not actually thinking about what kind of task they want to work with it. Okay, they did not. They just try to put, just like what the Word vet did. We put a lot of documents, so many documents inside, and try to train that model. But that document did not say, oh, this is for sentiment. So that is for emotion recognition. This statement suppose it should be happy. This statement suppose it should be sad. That statement suppose you should be angry. No, we do not actually train something like that. We just utilize the word to vet approaches like that. We try to know what is the surrounding word and try to get a vector. So from a lot of people's point of view, even these models already been trained, but we still call them pre-trained. So why is called pre-trained? Because they are not trained for our task. Not for our task. Not for our task. So then from assume here we having a user B. User B. He actually got this model's all the parameter and copy paste. See? Let me try to use a different color. Copy paste. Things right here. Shoot, shoot. Okay. All the values are identical from that one. So we actually would say the user B got a pre-trained model because that model is kind of already copy all the parameter value from the company's A setting. And we got this pre-trained model. And then afterward, we say we try to transfer them. Okay. What the did is like a user B actually probably collect a very small data set, this small, a lot smaller as compared to before. And then we actually tell this model, we try to train this one. After we train, the model change because some of the parameter value actually will be changing. And then after that, we change to different color right here. And then we can actually say this model, after they become blue, we call them fine-tune. Fine-tune. Fine-tune model. Why? Because this model actually trained based on this green data set, and our model are adjusted for that green data set. So next one, assuming this data set is talking about some emotion, like I actually say, when some people doing like, I'm really, really angry, actually is referred to angry, okay? Or like you, I'm very satisfied with what you want to do. We consider that as a joy. Then afterward, that we can utilize this fine-tune model to actually to detect all the emotion in people's statement utterance. Okay, so that is a way that we can try to talking about the language model. So the language model, we usually can see when the company try to working on them, and when we get it, it's more like a pre-trained model. Why we call them pre-trained? Because it's not being trained for the text that we are going to use. But when we try to get that, and then we can work with our data set and then adapt it a little bit and get some fine-tuned way and make our model more related to our task. So that is more fine-tuned one. And then right here, we have so many different language models, like from FastText in the 2016, and Transformer, and GPT, Elmo, and Bird, and so many different other the parts, or like right here, we have so many things, so many. And then in the end, you will find out I already lost counts because too many language model and too many. And right here, we can even show you some screenshot. And then right here, that is a timeline about our language model. And then this language model, actually, there are certain things for you to pay attention to. And then one is about this line, the purple line right here. Okay, the purple line right here represents human expert. And the blue line right here represent that is the ear. So why we actually say this one is the one you need to pay attention to? Because if you actually see this purple line right here, or actually you see around like 2022, we actually mark the 2022 as a pre-2022 one, is because you can actually see the GPT actually show up around here. Okay, before GPT come along, then ChatGPT come along, actually we'll find out that most of the language model, they are not performed as good as a human expert. They have a huge difference. But even though they have a huge difference, GPT-3 right here around that time, people already consider that it's too powerful, dangerous, because it's so dangerous. No human being or non-trust human being shouldn't access to this GPT-3. And after like few years, and then you can actually see people try to working very hard and to make the ChatGPT less threatened and then release to public. Okay, but then even when we having the ChatGPT, a lot of people already very satisfied with it. It still have a huge gap as compared to human expert. But then you actually can see there's a curve right now. Okay, so let me erase. You can see a curve. Let me try to slice this color curve right here. That is how we see the trend about the ability of large language model right now. You actually can see we already suppress the human experts' ability, getting much better. And as particular after 2025, most of the language model are actually closer to that part. So that is a very dangerous one. And then, so that is why I think a lot of people, if they try to study particular computer science or some machine learning related, you really need to know the concept and what is the limitation and the drawback about the language model, because later on, and then we need to be better than the language model. How can we do better way? Utilize different approaches by doing that. Okay, so that is again language model. You have the stage one on pre-train. We call them unsupervised. Okay, so some student also actually say that, Professor, I don't really understand this keyword unsupervised. Why is called unsupervised? Because unsupervised means that I did not train for the task that you're talking about. So sometimes word2vec is being considered as unsupervised. Even though when you see that, you actually know there's an answer and there's a context. We're talking about target word and context word, but you can still see some people consider word2vec as a unsupervised. Why? Because the answer, we did not provide the answer like the vector for the word marvelous. Suppose it should be 0. So for example, if that should be the answer, then I actually need to say good. Okay, I should having some human expert saying the good actually equal to 0. And 0.5 and 0.6, and then I need to having so many dimension. Okay, so if I can provide a data set look like that, so marvelous having certain vector, people consider they are more like supervised. Okay, but then because word2vec actually trained in a very weird way, right? And then after that, we got the answer, but the answer we think is really good enough to present the vector, but the human being did not provide the vector answer. That is why sometimes people still consider them as unsupervised learning, even though they already in a very strict way to convert their task to some supervised learning, and then you try some intermediate result as their answer. Okay, but then no matter how language models, people still consider them as unsupervised because we don't actually provide vector information. So in the stage one, we have this pre-trained model. In the stage two, we fine-tune them, okay, with the label information we want. Okay, so then that will be it for the part I've tried to record it. And the next one, we will come back for understanding what is called recurrent neural network. But then before we talking about the language model, actually many people want to talking about certain language model designed by utilize recurrent neural network. Okay, it is more like a very promising technique when they've been introduced. Why? Recurrent neural network actually is trying to design for having some sequential information. Like when we try to read this statement, design for obtaining language model.
Okay, when we have the design, actually my next word is for. And design for what? Then obtaining. So that is the next one. So all the things are come in sequentially. And so then they actually design RNN. Actually, if I illustrate that, it will look like this. Actually, the RNN is this one only. Okay, when we're talking about unfold, it's for you to understand how it might look like when we try to train it. So the first one actually is at t time minus 1. And the second one is at t time at t. And then the third one is t plus 1. They're like a t minus 1, t plus 1. That's it. Okay? But then what we meant is, so for example, if you're having a statement, like right here, we say design for obtaining language model. And at the very beginning, I input design. This is design. And then they actually try to tune in, the parameter will actually try to tune and say, what is the next word? And the next word, actually right now I say, but the next word, actually when you have the design, next one suppose it should be for. Okay, so then after they know it, they keep on changing the parameters. And then after that, I just input the third one, obtaining. So you can see this one, T is for, and this one is obtaining. So you can imagine, no matter how long the document is, the RNN mechanism can totally capture them, right? Because it's just about the sequential time. They come in, second, third, 4, 5, 6, 7, 8. So their memory actually is very economy. They don't need to having so many things to talking about the long language word. They actually can do everything in this one, but everything need to come in a sequential way. That is RNN. So far so good? Okay. If you do not understand anything I'm talking about, because I did not give you any equation, but you just need to know RNN actually, the whole word actually should be coming right here. So that is the next word, next word, next word coming right this part. Okay, so then when you try to train the language model, first you get a very big corpus, a big training data set. And in this corpus, you have all the sequence of the word. And you feed them into this language model one by one. Okay, so all the loss function, we say that is a cross entropy. By the way, you don't need to care. It's just saying that they actually will predict certain word, and then the true next word, and then they will try to adjust based on it. And then after they finish all the corpus, they have this RNN language model. So far so good? So you can imagine right here, I want to show something to you right here. You can imagine before 2017, most of language model, if they propose, utilize RNN approach, not the transformer approach. And then most of linguistic people thinking that RNN is the answer we want to looking for. However, okay, the RNN actually is in practice, we will find out that because every statement, you can imagine, if I want to, I already in the language model, I want to go back right here. I want to know how the design suppose it should look like. I need to forward back. But then the parameter value already changed, right? You can imagine, that is the difficulty. Because everything is like time series thing, so when you update them, what is the previous one? You can imagine if you have a long corpus, after you do everything right here, and the beginning of the part in your passage is the least significant one. Right? So only the end part, because the end part is a very new updated parameter. It's really related to end. So you can imagine the disadvantage of RNN, actually, they actually give high weight for the later word than the previous word. Okay, so it will also be very, very difficult for you to access the information in the very beginning. So that's what part we want to talking about. But they have the advantage, like they can process any input, and the computation for the step T is like from many steps before. And so model size did not change. and they can actually utilize different weights, same weights, and apply for every time stamp. So it would be very, very convenient for you to train RN. A lot of people around that time think RN is our answer. But there's the next paper coming in. I want to talking about this answer, this one. Transformer, I believe, actually is because around that time they have a big movie called Transformer. So you know the Transformer looks like, right? So it actually from the car to become the gigantic machine robot. And but then I want to talking about that person. This is a one person. No, I want to. Okay, so this person actually his family, his father is also linguistic. His father is very senior as compared to the son. The son is not that senior, that famous. But he tells the father, say, I don't think RN is the answer. RN is weird. Tell his father, something like that. And then why is weird? Because then actually only the later statement are important. And also, I believe the language is not just sequentially broadcast all the parameter. Some word is more important than other word, even though they actually show up in previously. So that is what they talk to the father. He said, I think the language doesn't look like this way. And he actually have exchanged the opinion with the father. Father said, I don't believe you. I don't think it will work. Son, believe me. I have more experience than you. You got to trust me. Luckily, the son did not trust the father. So next time, if your mother say, trust me, I know better than you. They're just thinking about Transformer story. The son actually thinking about, I still feel RN is not good. And then in Google, they're having some policy that you can working on some project you want to work on, okay? And then, so then he actually thinking, I want to develop certain language model. It's not based on RNN. And he has certain thought about that. And then afterward, they recruit certain people with them, and then they talk, and then talking about, yes, the model we tried to talking about probably will be better than RNN, okay? But then, no matter how they did, okay, they tried, so they recruit many people right here. It's not too potent. They recruit many people right here. You can imagine, those guys are more like junior employee, junior in Google, okay? And they write their code, and they try on that, and then they believe the thing, that the ideal of them is correct. But for some reason, the experiment result did not show like they're expecting. And then they have the discussion on, and in cafeteria, and there's this person coming in. I put 2.7 billion because this guy is his worth is more than 2.7 billion. This guy actually, he's more senior than the rest of the people, and then he actually could be worshipped as like a coding god in the Google. He have ability to coding in a very pretty way. So then he talk to those person and listen to this young employee talking about. And then as a senior guy, sometimes a senior guy don't pay attention to junior, right? But this senior guy is not any person. He actually do listen, and he feel like what they say makes sense. Okay, but they're just talking about, but then how come the experiment result did not show that way? So after he listened to that, he said, okay, how about that? I write the code by myself, because he's a god of the code, right? He write everything on his own, and after he rewrite the code, things work perfectly as they expecting. So right here, we want to tell you one thing. A lot of people talking about vibe coding right now, right? A lot of people tell you, oh, vibe coding is our next future, and then believe it. Vibe coding cannot write as good as like Jacob or Nikki or somebody. But then just imagine, at the time when they tried to write Transformer, it did not look right. You wait for the code of God to rewrite everything to make the thing correctly. So that is the answer also to tell you that please don't believe anything from AI. Okay? Sometimes the people have experience, know how to code them correctly. Some code look almost identical, but with tiny different details different, will make all the code different. Okay, so then you need to thinking about, you need to having that ability. When AI write a code, you need to say, no, this part is wrong. And then if you are that person, you can worth $2.7 billion. Okay, why we actually keep talking about $2.7 billion? Because that person feel like Google is so boring, so he quit the Google's job and go outside to create his own startup company. Because of the reason, Google really, really want him back. So the way they try to have the deal is, how about I purchase your startup company in $2.7 billion just because I want you to be back. That's what I feel. Of course, they will say, startup company is something. But then that is why I say he actually worth $2.7 billion. Okay, so then I actually put a mark right here. Transformer, this paper have a name called Transformer Attention is All You Need. Why is like that? Oh, I don't have it. Because there is a song from Beatles. Unfortunately, I cannot access to it. Beatles. You say yes, I say no. You say okay, fine. I don't have the song right here. But that is some Beatles song. Just know that is a Beatles song. Okay? And the Beatles song, online maybe have the song, but that's not us. Right here. Love is all you need. And then they're writing the paper in the last minute, and they cannot find out what is the title they want to do. And this guy actually really loved Beatles song, so then he have a joke. So how about we can have a thing called attention is all you need. That is a joke. And then to his surprise, all the people agree. So then that becomes the name. And then that interesting part is because that's a joke. And after Transformer become famous, you'll find out so many papers have the similar style. Have the title, similar style thing. So interesting part about that. Okay, so attention is all you need. What is attention? Okay, attention actually, right here, here's a statement. She is eating a green apple. If you actually pay attention to apple, okay, then which words are related, strongly related to apple? You might say that apple is strongly related to eating. Okay, but you can also say that eating actually should have, you can actually, from this example, you know one thing. In RNN approach, okay, and because actually we're doing something like that, right? So then we have the next statement. So from RNN approach, eating, suppose you should having high correlation to because is actually directly next to eating. But then from the transformer, they say no, eating is not really related. They are eating something. They are eating apple. So eating, suppose you should have higher attention to apple. Not to green, not to it should be to apple. Okay, so you can imagine right now from this illustration, it actually tell you the difference between RNN to attention mechanism. Attention mechanism allow you to having different way placing. It's not only related to how close these two words related to. RNN is not. RNN is like a surrounding word have high tendency. Actually, the word actually is longer enough, they usually have no tendency. So that is one example we have right here. We can have another example. The animal did not cross the street because it was too tired. You actually can see right here, we see the call reference resolution, right? You have this eat, an animal, okay? In traditional NLP technique, we need to utilize call reference resolution to refer to it. But in attention mechanism, they can tell you, okay, it actually is related to attention, related to animal, so their attention value actually is high. Okay, makes sense. So you actually can find out the attention mechanism somehow also addressed to the old problem, like coreference solution in our in the previous work. So how the attention mechanism looks like? Actually, this is the structure illustrated from a paper. I tried to copy paste from that. You can actually see right now you have the animal did not cross this one, and then so you can. But I usually when I show this one to students usually don't understand about that. You can imagine the attention mechanism is like here is the input. Assume you know the input is every word, so many words, different words, many different words, okay? And what attention mechanism is they actually having something like this one, almost the same size, okay? And then in this same size, they actually will say, this is a word, the A word, and then it actually related to that, related to this, related to that, something like that. So you can imagine this attention mechanism is like some buffer in between your input word, and then they try to refer to something. Does this word actually relate to have higher attention to me? So all of them are just like value. This a very tiny buffer actually have the value to this. Okay, but then in order to speed up all the calculations, so they utilize a lot of matrix way to actually do this matrix multiplication in a much easier way. Okay, so that is first, that is called attention mechanism. We actually will show you some example later. Just knowing that is a buffer, try to indicate what is a strong or is a low attention from one word to another word. Okay, so next one. Transformer not only having attention mechanism, transformer have two type of the structure. One structure is called encoder. One structure is called decoder. And then you can also see transformer. The reason we call them transformer because they can translate your language. Like your input is English and your output could be Mandarin. So that they transform from one language to another language. So you can imagine encoder corresponding to know all the information in English. Decoder corresponding to all the information in Mandarin and how they be mapping to English. Right? Understand about that? So then because of that, you can see your encoder will design certain things like they having some self-attention within this word. Behind the self-attention are just a traditional neural network. And then so they have different layers. One layer is attention, one layer is a neural network, that is encoder. Okay. And then this is decoder. How the decoder looks like. Decoder actually will having one attention, one is called encoder decoder's attention. What does that mean? It's trying to know the mapping between the English to Chinese. That is what you need to know. So you can imagine the attention. I need to know how this one, for example, like this word, are you hungry? And if you're Mandarin well, you will say this ni, actually suppose it should be you. So I need to having some attention to know, oh, this ni is related to you. So that is decoder encoder's attention. But then I also need to know my language. So the language in the decoder part right here, that the self-attention is trying to know the information inside this one. So decoder have two different attention mechanisms. Encoder have one attention mechanism. So far so good? Okay, so then go back to the attention. After you know this one, so then the previous example, the animal did not cross the street because it was too tired. You can imagine, like the attention is just like the buffer, as I say, okay? In that buffer, when we try to mapping to eat, then you eat will actually tell you, see, the animal have higher attention value. And some other value actually are lower. So right now, based on the dark or light of the color, you will know how strong the attention is. So that's the first thing. And second thing is transformer also know that you need to do multi-headed attention mechanism. So not only one attention, because you can have different angle, like right now. And this is actually have one attention about that animal. Maybe that orange one is for the co-reference resolution, but the green one is for what? It's for like the status of that animal. It's tired. So that have multi-head attention. So how many head? Later on in the other language model, we will try to show you. They probably have 16 or 24 attention head. That is why we say the language model consumes so many energy. Right? You can see every attention, they need some way for you to training, starting from initial value, but so many attention, they need to train in a very big corpus. Okay, I hope that is clear. And then, so right now, after you know about it, let's try to have some summary for you to compare what is RNN, what is transformer. I think most of the answers already mentioned, but then it's worth for you to review them again. about that? Okay, let's try to see this one. This one is just trying to know if you understand the specific characteristic between one thing to another. So when the processing the sentence, this is a marvelous movie theater. Which model process words strictly in order from left to right? That is IN. Okay, so the transformer actually we're actually having the different. They can jump in between them, but IN actually need to do only can do that sequential. Which model can directly connect the representation of the first word this with the last word theater in a single computation step? That is transformer. Okay, so you can actually see the advantage why the transformer in the end become the leading mechanism. Okay, next one. Which model has a harder time remember the long-range dependency, such as connecting this and the theater when the sentence is very long? That is IN. Okay. In terms of the parallel computing, by the way, here that is certain thing that we did not talking about in our class because I want you guys try to know if you can understand about that. Which model can process all the words of this is a marvelous movie theater simultaneously? The answer is transformer. Okay, so in other words, RNN is not good for parallel computing. Because you really need parallel computing is can I actually compute the different thing at the same time? So can I actually compute this at the time t and is at time t, marvelous in time t? If I actually in the time t, there are 3 different lines for me to process at the same time. That's called parallel computing. But RN cannot do that. RN because every time is based on the different sequence, so it can not actually really speed up. Because you do not allow the possible way to do the parallel computing. But the attention mechanism in the transformer could, because you can actually process it, and you can do the multi-headed together, different headed together in the different parallel computing way. Or actually you can try to go for attention for different words one by one. You can actually say, I can have different units. One responsible for this, one responsible for is, one responsible for marvelous, and so we can do that everything together at the same time. So the training time will be a lot faster than the RNN. Okay, which of the following statements are correct? Okay, the transformer can directly compute the relevance between marvelous and movie theater. That is correct. Okay. RN compute attention weight across all words simultaneously. You need to know that is wrong, right? Because the RN do not have attention. At least when you see that, you say, oh, it's wrong because they don't actually have the attention weight. RN rely mainly on the sequential memory rather than pairwise attention. That is right. Transformer replace recurrence with self-attention layer. Yes. So remember the R is stand for recurrence. So they utilize recurrence for the self-attention. Why are the transformer more scalable than RN for a long sentence like this is a marvelous movie theater with excellent sound and a comfortable seat? Okay, why is more stable? Because they can process all the token in parallel. So then from the way they try to compute is more stable. And then remember this one is wrong because transformer require large parameter, huge parameter, not less parameter. RNN actually have fewer parameter, but transformer have a lot of parameter. They use self-attention to connect any pair of the word directly. This one is right. And they are unaffected by sentence length. This was wrong. Only RNN are not affected by sentence length. Transformer need sentence length. Because you can imagine we need to have the buffer, right? You can see every attention mechanism need a buffer. So that buffer define, so for example, if you say 1,000 token, which means that you can only allow input at 1,000 token, then have 1,000 tokens of attention head and so many different things. So the size is being fixed. And of course, the later on, like ChatGPT and so many mechanisms, they utilize different way to somehow make this one become unlimited. But that is later part. Transformer, and originally when they designed them, they having the less capacity. Okay, so far so good? Good, so then we finish about this quiz. Then we actually give you the class lottery right here. By the way, the answer is also transformer, okay? Try to make sure after today, with lottery, with the session, you definitely will remember what is transformer. Okay, so? Okay, so next one we are going to talking about bird. Bird, actually, when they actually having the bird, originally, they did not, I guess they probably did not thinking about this dog. But then I want to say some joke. I think students usually love joke. So then, that is the joke I want to talk about. Where is my joke? Here is my joke. Okay, so you can actually see right now I have several cartoon, right? And then you can actually find the transformer from the movie, okay? And then you actually find out 2018, around that time, they have another language model people will consider they are so good. The Elmo model actually utilizes Alan, and I'm not so sure did they do the transformer. And then it's called Elmo model. And then Elmo actually from Sesame Street that belonged to that puppet. And I remember when I actually I went to attend one of the top tier conference called EMNLP, and every attendant actually received this puppet, Elmo puppet, because around that time the conference leader believed Elmo is the future. Just like Alan, people believe they are the future. So when people tell you this one future, don't believe them. Things will change. And then after like 6 months later, or 3 months later, Bird come out. And Bird actually is that puppet, also in Sesame Street, right? And then, actually, we also have the Roberta, and then we also have that around that time, so many language model actually utilize Sesame Street's model, okay? So then there have around 2 years. In the NLP community, we have a joke. Because Transformers say attention is all you need. Our joke is Sesame Street is all you need. Because all the models actually come from Sesame Street. Okay, that is my joke. I feel the joke is so interesting. That is why I'm always talking about that. And where I heard from that joke? I heard that from Professor Gao Hongyu. Okay, it's like, ha ha ha, so fun. And then I guess he did not mention that in his class. I still mentioned that in my class. Okay, and why is it called birds? Bird actually is another transformer. It's just a simplified transformer. Okay, because transformer originally when they design is called unidirection. Why is it called unidirection? You have the encoder block right here, decoder block right here. Here is the input. Here is output. So that's only one direction. Okay, and then some people actually were thinking about, some people also in Google, thinking about, can we make the transformer smaller? And then if we can do that, can we actually learn all the important thing about that particular language we want to learn? Then not try to mess up between two different language. They try to only emphasize on one particular language. So when they try to working on that, is actually you can see from their name, it's called bidirectional encoder representation from transformer. In other words, what they did is they only get that part. They only have that part. They delete the decoder part. Okay? It doesn't mean the decoder are not important, because GPT utilize decoder. GPT or ChatGPT utilize decoder. BERT only utilize encoder. Why encoder? I guess around that time that you're thinking about, if I just encoder, I only emphasize on the language I try to pay attention to. I don't need to talking about something else. That would be good enough. But why people actually utilize decoder? Later on, we will try to talking about why they utilize a decoder. Because decoder actually is not only about the language. Decoder also try to pay attention to your output. The language to your output. Okay, so then if you actually more emphasize on generate something, you will find out most of the language model they utilize decoder. If you do not talking about, you don't want to emphasize on what you generate. You emphasize on like this language, anything I want to know about this language, you utilize encoder. Okay, so far so good. And then, so most of the language, everything they want to working on almost the same as the transformer because they have the same architecture. But BERT become a very, very important paper. Why? Because that is the first language model try on different tasks. Most of the language model, when they try to propose, they try on like 1 or 2 tasks. Okay, BERT did not have any invention. Okay, the only invention is like, how about we try to having so many different tasks together, and I can show you they are really a generalized language model. But then the BERT actually have two different version. One is called BERT base. One is called BERT large. What are this BERT base? It means that it's a small model. Small. This is large model. Okay, and then so you can see how small. First, BERT base only having 12 layer of encoder. Okay, BERT large have 24 layers. Okay, and then people later on find out the more, the later, the better. So that all the language model, I have to say, that let me try to do something back. Shoo, 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 right here. Where are my fancy figure? My fancy figure. Shoo, shoo, shoo. Here. They are all fancy figure, right? Okay. So you have so many names. By the way, most of them are just transformer model. Just transformer model. But they maybe do some tiny different, changing a way how they try to train, and the way they have to train differently, they give them different name. Okay. And then this model actually have 24 blocks. That model say, how about me? I have 48, and then have another name. So then that is why they have so many different names. But in the end, they are almost the same. I mean, the model base look the same. Of course, you are belong to that company. You'll be angry to say, how come I'm not the same? No, you are the same. Okay, from data mining perspective, you are all the same. Okay, then you can also see that how many attention head you have. 12 attention head. And in BERT large, you are 16. You know, sometimes my students are asking me, Professor, I can understand that large is big, but when small, actually, it looks like they cut in half, right? So why not cut in half to 8? And have you had that question? You guys? Okay, let me try to tell you how to read the paper. Why they need to have the large one? Because they need to having some output is better than any model they can thinking of. Around that time, so what they did, they need to increase the parameter size. People find out by increase the parameter size, actually you will get better. So then they want to have, but they know the size is big. You know, bird large is so huge. There's no way you can run bird large in your computer. That laptop, no way. You really need to have a GPU having a high memory capacity to run that, okay? And, oh, by the way, when I say there's no way for you to run the bird large in your computer, it's based on my experience like 5 years ago. But with Moore's law, probably you guys can run that right now, okay? And but they actually want to make this the model smaller. And when the model actually gets smaller, you will know that the performance was not that good, okay? So then they are tuning their parameter to make sure the model are small, but they still can outbid other things, so they will consider the best, okay? Why they did that? So they can actually, around that time, you know what they try to compare with? They try to compare with the GPT, okay? GPT utilizes a decoder, okay, and OpenAI around that time. It's GPT-1. BERT actually tried to compare with the GPT-1. And then the bird large tried to compare with all the model that they actually know around that time. So they have different model size. Next time, if you see certain thing, you need to know they are trying to be tuned in. But this part is the one I feel interesting. Okay, so in the transformer, they did not tell you how they get the input. You just know the input have the word. Okay, bird actually is more delicate than transformer because their input actually being changed. So you can see their input has 3 different types of the input. One is called token embedding. One is called segment embedding. One is called position embedding. What does that mean? Segment embeddings mean the bird actually can input 2 sentences in 1 input. Transformer only do 1 sentence, okay? BERT do 2 sentences. They will try to tell you why they do 2 sentences. And then after that, people will say, oh, if that's 2 sentences, I can do 3 sentences, I can do 4 sentences, okay. The longer, the better. But around that time, you have the memory capacity problem. And the token embedding, we will also try to talk about later. And position embedding is about the position in that sentence. Okay, so then let's try to do the token embedding. So what they did is they tokenized the keyword. Have you remembered the tokenize this concept when we tried to talking about previously? We're talking about stammer, right? We say that if you do not do something correctly, if you type the whole keyword with the ed, with the s, it was difficult. So what they did in the bird, they kind of try to reutilize all the language, the processing, in the NLP processing, they have certain technique to do that. They utilize that for the tokenizer. So you can imagine they have a lot of pre-processing before they training the model. Okay. What they try to do the pre-processing, they do stabilizer. So what they did, but stemming is like they remove them. But the bird say, I don't want to remove them. I just try to separate them. So you can see there's an example right here. We say the dog is playing, okay? Instead of just remove ing, I segment them into the second token. And in the second token, I having some specialized symbol to indicate that a certain thing being stemmed from the previous word. So then you can also know the relation from it to another. So that is, they do some tokenizer. And tokenizer also become one very important mechanism in a lot of large language model. Some of the different language model, they will have different way of do the different tokenize. Okay, so they do have a different way to tokenize them in better way. And also, not only that, because the bird actually allow you to having 2 input, 2 statement, 2 sentence. So I need to having some symbol to represent that is a separation between the previous statement and the next statement. So they have this symbol, separator. That is this symbol. Next one, they're adding another token called CLS. What's that for? You can imagine, right now we say the bird actually is bi-direction. So you can read from here, you can also read from here, okay? But I need to make the machine to know where is the start. So I have this CLS as my start. But later on, people find out they have advantage about having this CLS. Okay, so what they did is they tried to train with two different tasks. One is closed task, the thing that we learn when I learn English, I hate English subject. I hate that. My English is so bad, so bad. I tell my students I'm so bad. Why? Because my class teacher always like to do the test, utilize closed text, and then they have this textbook and cut out so many things and ask you to fill in. If you did not fill them correctly, you get wrong score, right? I always cannot fill in correctly because I never memorize the text. I just like they have so many things I can learn. Marvelous, good, bad, and everything I can learn. So I actually try to input different things. It's wrong answer, okay? And then I'm guessing that the person who invents this training probably also suffered my problem too. The class teacher actually give them too many class texts. And so what they did is they try to transform their trauma into the machine. you will find out so many training things actually come from our real life experience. And then they ask the machine to guess what are the words right there. They give them so many surrounding words and ask them to get the correct target word. And that is the first one. The second one is called next sentence prediction. So first one, in the text, LM closed text, what they did is you having some document. So do preprocessing again, and in that preprocessing, they randomly mask 15% of the word from your document and input them into your system one by one. Okay, so 15% of them actually was marked and randomly. So it's not just like word to vec, say surrounding in and then sliding window. No, they actually just randomly pick the word right here in their document. And not only by that, okay, and then you will actually find this is the next interesting part. I felt like 18% of their training time is utilize this mask token word. So 18% of the time, you try to train on this 15% of the thing, okay? And in 10% of the time, those mask words actually are not having the simple mask. They've been replacing by some wrong word at random. Do you know what I mean? It's like I am not only giving the perfect solution and then the question to the student. I also give the wrong information to student. I give wrong information to machine. Do you know why it's important? Have you heard about some master or some your family member, senior member, talking about they will just keep on saying that 一代不如一代, so that the generation, every generation get worse by every generation. They actually were saying about that. Why? Because you did not train them correctly. You know, a lot of masters, what they did is like they know 100%. But if I teach you all the 100%, I'm out of my job, right? So I only teach you 90%. And because there are 10% of essence that you did not know, and when you did not do better, then you still come back to me, ask me, Master, I suffered that problem. What can I do? Okay, and then afterward, you will find out that the second generation actually get last, and then the second generation utilize same philosophy, only teach 90% of them. So then the third generation only get 81%. So of course, every generation get worse. That is one possibility. The second possibility is sometimes our student, even though I give them 100%, okay, but I think I teach them 100%. There may be something that I don't know because it is not occur to me when I teach. But then you just memorize everything I say. Is there anything that happened to you did not come from me? You lost track. You don't know what to do. And around that time, maybe you come back to me, say, Master, what should I do? And I say, okay, give me $100 first, and then I will teach you, something like that. But then when we try to train the language model, we find out something. Do you remember the problem of overfitting? Remember what overfitting happened? Why the overfitting will happen? Because the machine just memorized everything. Okay, so right now what they did is they say, how about I make sure machine actually will know they should have memorized. They should digest before they learn. Some of the words are wrong, so I add some incorrect information during my training data. The machine need to know which one need to be removed. Okay, so 10% of the time is they give them this poison information. 10% of the time is they give them the answer directly. So 80% of the time, they have this phone. Is that me or not? Let me check. 我还是有在线上哦，是哦。我刚刚有听到声，应该不是我哦。Okay, and I try to make sure I'm still online, right? Okay, good. Because I heard that something like lost connection. So 10% of times I give you the answer directly. Because if I did not give you the answer, you might lost clue. Okay, so you can actually see the bird actually tried to do something very interesting. Okay, some of the way they can do is can be alleviated, reduce the chances of overfitting. Sometimes they do also give the clue to the machine, say that is the answer, so 10% of the time. So in the end, the machine, right now, this large language model probably can perform better based on that kind of training. Okay, so that is the first task. The second task is called next sentence prediction. What they did is, for example, you have two sentences. Okay, the man went to some store. He bought a gallon something milk. Okay, and then the machine need to know is that the next sentence is he bought a gallon of masked milk is a next sentence of the previous sentence, the man went to a mask store. So that is the next sentence prediction. Or actually they can probably do something like the man something to the store. And then you randomly add certain statement afterwards, say penguin something fly. And the flying bird. Okay, so then the machine need to know that is not the next statement. So when they did this one, they think, okay, the inventor think, by having this next sentence prediction, I will be able to teach the machine to do inference. To know that the sentence actually have logic information between them. Why is that important? Because then later on, when they actually try to measure how good they are, they need to perform well. So in the second training one, they actually give the 50% of the time they are the real sentence, followed by that. 50% of the time they give them the random sentence. And then they'll find out the pre-trained model actually can almost get them correctly. Okay, so that is a part try to surprise most people. And then they utilize 6 different data sets. Okay, some of them are for inference. Okay, you give them 2 sentences, and then they try to tell you this sentence have what is a logic relationship between these 2 sentences. Are they entailment? Entailment is like, are they next to it, supported, or are they contradicted to each other? The second statement contradicted the first one, or actually they have no relationship to each other. It's called neutral. So that is the first inference problem. The second one is called textual entailment. It's very similar to the ML as the first one. And there's one called QQP, is for to knowing do you actually input the same question. And the fourth one called paraphrases. So actually you have 2 paragraphs and want to know that these 2 paragraphs are almost the same. And the fifth one, natural language inference, is like you give a question and a paragraph to see does this paragraph answer the question you ask. Okay, so you can actually see there are different kind of tags. Then the sixth one is talking about the paragraph similarity. So they have 6 different benchmarks. Before, people did not actually mixing. For example, if they do inference, they probably will pick the first one and second one, and that's it. Okay, and if they do question pair, they probably will do this third and a 5. So you can imagine what the bird did is they actually put different tasks in the same comparison. And in that comparison, they told you, ta-da, okay, my bird large is the best. Okay, you can also see there's a certain thing called SOTA right here. Right now, a lot of people utilize this terminology. SOTA is not a method. SOTA is so many different methods. SOTA means state of the art. So what it means is you don't have a method actually having 60.1, 82.3, no. You have some method do 60.1, they have the best answer. Another different method do 82.3. So by combining all the number right here, you call them SOTA. Okay, so that is why right now in the current machine learning world, you will see a lot of SOTA. And where is the SOTA? No, SOTA is not a method. It's a lot of different methods. And then you can actually see this one. They say bird base is better than GPT, and bird large is better than all the method. Okay, so that is the experiment, and that experiment really wow so many people. Find out, oh, we can do transformer in that way, okay? And after bird, so many language try to know. You can actually find out that actually getting better and better and better. That's the interesting part. Okay, so we're already talking about so many birds right here. Right now it's your turn to reflect what I say. test finished? Okay, so then let's see. The diagram illustrates a simple input of the bird. Can you identify the NLP principle applied in it? Every year people were actually confused by me. Okay, first, lexical analysis, because you need to know that, for example, like right here, play ing, and some of the word right here, for example, they need to do certain lexical analysis before they can do the stemming. Okay, so lexical analysis and stemming are actually being used. Next one, word segmentation. You will find out that many people actually fill in the word segmentation, but I did not mark them as a correct answer. Why? By the way, that is for me to remind you. When we're talking about word segmentation, we're usually talking about certain language, and their word do not having the very clear boundary. So then we need to somehow knowing which word actually belong to that. So that word segmentation is for the language. They really need to do the word segment, like the Chinese or like Trigrina, right? So they need to do word segmentation. Right here, that is not called word segmentation. We call them tokenizer. We call them tokenizer. We don't talk them word segmentation. So that is a way for me to tell you, yes, it looks like a segment, but word segmentation is for the language who need word segmentation. Right here, they do tokenizing because supposedly play ing actually don't need to do the segment. Okay, how they actually being separate because we utilize tokenizer to working on that. So the first one is a little bit tricky. And then you did not see text categorized. You also did not do the call reference resolution. And so that is why they are not answered. Next one, why the bird used two additional tokens, CLS and SEP, as its input. Okay, and well, okay, I mentioned that bird is bidirectional, so you utilize CLs. Maybe I forgot to click on it. And the need to segment the sentence is for SEP. And during the inference ability, because you to do the two sentences to be together, that is try to utilize SEP. And then I think I forgot to mark the bird is bidirectional. And then CLS can be used as an aggregate sequence representation. That is a part I said I did not tell you that before. CLS, let me try to go to this part right here. CLS, and then right here is actually as a beginning of the sentence to say that is a start. At the very beginning, we just try to mention about that. But then afterward, people find out the CLS, this one actually can learn another embedding, right? Because every token actually can learn some embedding. And people find out this CLS embedding actually somehow is closer to all the embedding and the cement together afterward. So they can be utilized as a sentence embedding afterward. That is an advantage that we find out after that. Okay, so I utilize this one for you to know can be used as aggregate sequence representation. So then afterward, when people do sentence embedding, they can pick the CLS as an embedding. Okay, so the next one, the bird's mask LM pre-training text, 80% of the instance are replaced with a word this, 10% this, 10% this. What's the purpose of them? All of them are correct. Okay, so then, but you need to know this is a very smart way to prevent overfitting. So sometimes overfitting probably is because we did not give them the wrong information. And that is why they will memorize all of them. Okay. So that is about the birds. But before I'm moving on to the next one, there's something I want you to know. Why the birds actually can be successful. Actually, you need to know, or like transformer can be successful. First, you need to know, because first, you have very large computer, good computation resources for you to learn everything. The second thing, you have large corpus. Okay, where the large corpus come from? If we need to go back to contribute to the who actually the one try to make our large language model work, you might thinking about maybe that is www. Team Berkeley have the triple W in order for us to share the information. So then you have Wikipedia, you have many people. Actually, many people put their information on the web. And those information on the web, and Google can crawl them. And all the crawling information become the information they want to train. Okay, but not only that. You know, from 1996, Google probably starting from, I don't remember where they're starting from, because two Google inventors, actually they are PhD students before. PhD student in Stanford. And what they did is they tried to working on some information, like try to preserve certain the information in digital way. Okay, digital archive, where you can thinking about that. And since then, Google starting to having a project called Google Book, or some people call them Google Library. Have you heard about that? You try to type what is the book you want to looking for, and then you type the Google, you will find out Google having all the information. They have sent the people to do the scanning and do OCR to get all the information about there. And then you can somehow try to say, oh, I have this quote, I want to know where the quote come from, and Google Library have it. So you can imagine Google itself have a lot of information because they preserve them for like 20 years. And then utilize all the 20 years information and all the 20 years the web information, and together to train our large language model. So it's not come from nowhere. The data come from a lot of effort before. Okay, so next one, we already talking about TF-IDF. We have the word2vec, we have Ireland, we have BERT. I did not talking about transformer because BERT is type of the transformer in a simplified way. And then interesting part is that is a statement I always like to tell the student. Buffalo, 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 buffalo. That is a statement. Okay. Okay. So there's a different word. The bear can climb tree. He cannot bear. And then Chinese word like right here. And we'll try to show you the Chinese word. First, you need to segment, and then you actually see 3 different words right here. Okay, they all belong to different meaning. Okay, so which technique you think the TF-IDF or word2vec actually can be used to understand this statement? Wait, let me see if I do something correct. I find out today. I did not do that correctly, sorry. So then, how about that? Let me try to add in workup right here. So if you actually on the word cloud right here, can you tell me which one you think can actually understand this sentence? Buffalo, 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 buffalo. And why not? So TF-IDF, word2vec, Ireland, BERT. Okay, if you find out they have different thing they could, and then try to have submit them in a different input. Okay? So, let's see. Only one answer? If you believe there's a multiple, so word2vec, can word2vec actually do this buffalo, 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 buffalo? Seven participants not typing. 5 people already participate typing. So then I don't got any answer yet. I only got BERT. Ah, great. I have a word2vec. Yes. Some people believe word2vec can do, Ireland can do. Some people think BERT. Okay, So we have 23 people already input, 25, 26, 27. So then, nice, you do transformer. Okay, we don't have the transformer in our option. Remember, if in the final exam, I'm only asking you bird, don't answer transformer. You got the dark point. Okay, so then right now you actually can find out, a lot of people say that bird, and some people think the word to vet probably can do, and no one actually talking about TF-IDF. I'm glad, at least you know TF-IDF definitely cannot help because they don't know the semantic meaning. Okay, and also TF-IDF, after they do the word segment, they do the back of word part, and all the buffalo become the same. So that is why they cannot do it. How about word to vet? Okay, word to vet, actually, you need to know how the word to vet try to learn. So for example, how I learn this and that, there are different meaning, right? One is a verb, one is a noun. Can word to vet actually learn that? The answer is no. Because for the word to vet, they are same embedding. Remember that they are the same one-hot encoding. Same encoding. So for the word to vet, this bear and that bear actually are the same, even though they have different meaning. So what they will get from the word to vet, they probably get certain average to see which word actually appear more. Okay, so you will find out bear is not really bear. Okay, and that is the difficulty about the word to vet. And then how about that RNN? Okay, RNN actually will try to do this and then and afterward like that. So maybe they could, but actually may have difficulty because that bear actually is actually consists so many noises. So maybe later on they have difficulty. So when we actually show you that example, you need to know one thing. In order for us to knowing that is different, this, actually you know this one is don't. The second one is where, and that is others that have different meaning. Okay, and then why? Because how I actually know them? Because they have the positions difference. So you need to having some categorized way, some embedding, allow us to know they are different. And then they're trying to go back to the reason we want to ask you is come back right here. Okay, so then this mine, actually you will actually find out my embedding is plus plus. So for example, originally my embedding assume if the one-hot encoding from word to vet is 0.1, 0.2, and 0.4, assume at the original one that my token embedding from word to vet coming back like this one to me. Okay, so this one might actually got this one. And segment embedding, I have EA. So assuming EA actually right here, I will actually adding another two. This one is just assume, okay? Give you some illustration. So then afterward, this embedding, if you are segment A, you got this 2.2. If you are segment B, you got 0.2 right here. And then position embedding, this is the first position. So assuming the first position, second position, they have the corresponding value right here. Okay, so then the first position right here, I actually will get, I'm sorry, this is quite math right here, but let me try to add it. Assume the position embedding for the first one actually is like 0, 0, and then right here, I just like 0, 0.1. Assume. And then if there's a second, then I will have 0.02. 3 is 0.03. 4 is 0.04. So you understand what I meant. So then when we adding them together, the final embedding will become 0.3, 0.2, 0.41. So far so good? Understand what we're talking about? So your embedding, you have token embedding, segment embedding, position embedding. You see the plus, they really plus them together. They're really adding them together. But then how to set up the value? Actually, they have some tiny way to do the adjusting. So you can actually understand, based on that, this keyword, like buffalo, 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 all the buffalo will have different embedding, right? Because you know the first buffalo adding the first position, the second buffalo adding the second position, the third buffalo add the third buffalo. So then actually your segment embedding is the same. So then all the position embedding is different. So we'll make the buffalo a little bit different from other buffalo. And after you learn from many things, so you will know, oh, the buffalo in the first position usually have other meaning. The buffalo in the second position probably have other meaning. So in the end, they will be changed. Understand? Okay. So then we say the bird can help. Because why the bird can help? Because birds have this position embedding. Okay. Okay. So I hope by that you do understand why those model actually can help. Okay. So next one. I guess I don't have the time to talking about GPT-3. It's 11:40. Fine. Okay, so 11:40. So how about the rest of them? I will talking about that next time. But I will see. I give you the last class lottery. I'm sorry for today's speed. It's slower than I think. Why is slower? Because we have audio problem. Okay, so that is our third lottery. And GPT and some other information, we're talking about that next time. And so for today, when you come back, try to understand how the bird and transformer try to work. And next time when we go to the GPT, instruct GPT and other Pegasus, then you will understand more. Okay, so let's try to do some summarize before we go to the 1 minute reflection. Today we're talking about name entity extraction. Remember, name entity extraction, you can find and classify all the name in the text, and then you can utilize certain rule-based approaches or machine learning approaches to deal with that. In the co-reference resolution, you need to identify and link all the possible expressions that refer to the same entity. And then we actually, the reason we're talking about that is we want to talk about bootstrapping approaches. And bootstrapping approaches can be utilized in different ways, including if you lack of the data, you can utilize some C to looking for more information. And then we also having some recurrent neural network is for the dense representation, and then all the input are dependent from the previous one and can process any length input, but it's difficult for you to access information from many step big bag. Okay, and we also talking about language model. Okay, we do not talking about the ChatGPT. Okay, we're talking about transformer. Transformer is multi-headed attention mechanism. They have encoder and a decoder. Please remember, the encoder have one attention mechanism, decoder have two type of attention mechanism. And BERT actually is like for a deep bidirectional transformer, and they only utilize the encoder. And when is the time you want to do the encoder? If you only want to know the language between themselves, you do encoder. If you actually want to do some generation, then do generation, you do decoder. So the ChatGPT, we're going to talk about that next time. And the BERT actually having the two different type of tasks, closed text and then sentence prediction. Okay, so that is the part that we try to cover for today. And here are the 1 minute reflection. I'm sorry that today we have mechanics some problem. We'll try to make sure we're not having that issue next time. And our TA will come back right here and then try to give you the lottery. Okay, so if you have any further question, and let us know.
Looks like we can do 29 and October 13 together.
Okay.
29.
So the first one is 1 minute reflections winner. We will pick the three. The first winner is 006 11060143. Okay. Next one is 111006220. Okay. Third one. Wow. 613470993S. Okay. So then we have class participation. Really? In class. Oh. 这很多人没写嘛。Oh, congratulations. Okay, next. Next one, 114065425. Who's that person? Congratulations. Is that the first time? Or second time?
Oh,
11. It's not the same, right? 06544. Who is that person? Yay.
we do 6.
You won 3 times already? Wow, you're lucky. You're lucky. Oh, 123700344. Who is that person? 耶，本来是谁？有一个人惊叹了一下，不然是你。114062530，谁？这个人，你在了吗？Okay. One more. Who is that person? How many times is that? 3. Okay. 1, 2, 3, 4, 5, 6. Then online. 113034611。你哦，好，不错。抽2次还是有好处的，对不对？That one is not belong to you. 这个。我在这里吗？没有。我看我的信号没信号。哦哦哦哦 ！You are lucky. You are lucky. We got at the same day. Go to buy lottery. Okay. Last one. Last one. Ah. Is that person here? No? Okay. Good luck next time. See you guys next time.
See you
Bye.
in class, Professor.